water for it to be effective, which makes it much easier to install, much easier to maintain than an ocean-based buoy. It of course has its disadvantages in that the ionosphere is variably sensitive in times of geomagnetic storms and at night, for instance, and that's why this is a good complement, a good augmentation to in situ sensing. The other interesting advantage is the fact that new receivers are able to track very many different constellations. There's not just GPS GLONASS, there's NAVIC, there's Baidu, there's QZSS, there's Galileo. So there's so many different constellations that any new receiver is actually able to see tens of different satellites at any given time, which also means that the entire sky is actually visible from a single station. And having these many links means that you can use relatively simple signal processing techniques to distinguish those signals. So as I had said before, we rely on a global GTGPS network. We actually have about 300 stations right now within Guardian. And what that allows us to do is cover almost 2/3 of the world, as you can see in this map provided here. At a maximum, we can cover about 90% of the world, but right now we have about 2/3. And with addition of strategic areas such as in Antarctica or in Russia or some of these islands in the Pacific, we can actually cover about 80% of the world. And this is again relying on that 1,200-kilometer viewing distance from any given station. A key advantage is the real-time nature of this network. So in any case, when an event occurs, it takes about 8 to 40 minutes for that signal to reach the ionosphere, depending on the propagation speed of the wave. In traditional processing, it would take you about half an hour to a day to obtain the data from these GNSS stations and then write your software and then look for stuff. Whereas in our paradigm, where we're doing the analysis in near real time, in 10 minutes, we are able to produce analysis and produce a time series for these data. So on our Guardian webpage, without writing any software, without any programming from the user, we're able to provide time series maps and hodochrone plots, which are essential analysis tools for ionospheric subject matter experts to identify these signals. In addition, with Scout, we're actually able to greatly reduce the volume of data that an expert needs to analyze. So this is the architecture for Guardian. This green box shows things that are operational, and the yellow box shows things that are being researched on. So the eventual aim for the system is that we'd be able to look at a signature in the ionosphere and say, okay, there is a tsunami with this much 1/3 wave height, with this period and this speed heading towards the land. And we are able to detect this on the open ocean where there are no buoys. So we have a substantial part of that already operational. So how this works is we get our data from the GDGPS network. We then combine observables to produce time series of TEC data. We have Guardian Scout, and I will describe it in more detail shortly, that then looks at these in the aftermath of a big earthquake and shortlists the signals that seem like they might have an earthquake or a tsunami signature in them. And so this shortlist is then passed on to the website, and the user who's using the website, and I'll show you a little demo at the end, is able to easily access these time series and look at the exact instant where they might expect to find a signal. We also deliver our data in a near real-time fashion to CDDIS, which is the NASA repository for ionospheric data. And so users can actually look at this data and train their own algorithms on it. In the future, what we want to do is also do inversion. So we want to make a connection between ionospheric signatures and tsunami properties so that we're able to invert for important properties of the tsunami so that we can augment like indentation maps and assess the risk from the tsunami. So this is very much an active area of research. We've done some preliminary work on it, and we continue to work on that. I want to spend a minute describing Guardian Scout because this is the newest addition to our online system on Guardian, and it actually greatly reduces the effort that a subject matter expert has to put in to review these links. So as I had said before, these new receivers often connect with tens of satellites at any given time. And so there's usually a large volume of data if you have to go looking for a signal. And so what Guardian Scout actually does is that it employs a convolutional neural network and searches for signals that might represent an earthquake or a tsunami and flags these for the user so that they can actually go and see a much smaller subset of links, which makes the discovery time much faster. So as an example, I have two signals here. One is from the Noto earthquake in January 2024 in Japan. And you can see this is an N wave type signal, and this came directly from the epicenter. And there was a very tiny tsunami in Vanuatu in 2023, where you see this wavy structure, which is more like a sine Gaussian. And so using those examples, those are actually the kinds of signals that we look for with the neural net. And what it does is it embeds these signals as synthetics in background data from any given station and trains the neural network to find these labeled signatures. And then once we have the weights trained, we actually turn that on to the near real-time data stream. So it finds similar signals for any given station. And so what this does is that instead of, say, looking through 100 links, we have to look through maybe 15 links at any given time. The interesting thing here is that we've managed to actually integrate this completely within the web system of the Guardian interface. And so it just enables the user to find signals so much faster. As I'll show you in a future slide, the experience of finding a signal is very, very quick as compared to before. So as a recent example and case study for the Guardian system, we have the Kamchatka event that I'm sure is being talked about a lot at this conference. So on the left here, you have the station called G027 that we have near the Kamchatka Peninsula. And what we can see is that it picked up an earthquake N wave type signature in about 13 minutes after the earthquake. And in addition to that, in about 72 minutes, we actually started to see a tsunami forming with this sine Gaussian type behavior. And so within 72 minutes of the earthquake, we actually had an indication that there was a tsunami that's going to form from this earthquake. Moving forward, a few hours passed, and then we were looking at the Hawaii area. And we have a few stations in Hawaii, and what we can see here is that the GNSS stations, again because of the geometry of this problem, were able to pick up ionospheric signatures about 30 to 45 minutes before any of the in situ tide gauges in Hawaii actually picked up a change in sea level height. So that would have, in operation, given us about 30 to 45 minutes of extra warning time, which is obviously very useful. Thankfully, this event was very small, and so no evacuation was necessary. But in the event that an evacuation becomes necessary, that extra time is actually very helpful. So we also published a little NASA press release about all of this. So you can scan this QR code and you will be able to see more details about this event. As a
Okay,
last thing, I
thank you.
want to show you a demonstration here of what Guardian may have looked like on the day of the Kamchatka event. So if you actually scan that QR code, this example is available on our Guardian website, so you can actually play with this yourself. But this is a movie, it's essentially a screen recording, just to show you how this works. So you see that there's a big earthquake there, and there were a lot of earthquakes that day. So you scroll down to the earthquake that you want. When you click that, it gives you a lot of information about the earthquake, magnitude, depth, time, solar conditions, and then you can also see the links that were active and directly plot from there, and you can get to the time series. And that black line shows you when the earthquake is, and you can actually zoom into that area and spot the earthquake signature. So this is almost going too fast for me to actually even talk to it. But we're also able to provide other analysis like hodochrone plots and maps that are very useful for subject matter experts in the ionosphere. If we shift our attention to Hawaii, this KOKB station is one of the stations where we found the GNSS signal that showed the tsunami signature. And so here too, we can actually see very clearly the emergence of the tsunami signature. And again, this was about 30 to 45 minutes in advance of the in advance of the detection of the tsunami in the buoy. And so you will see here. And so from days of analysis, this has gone down to the time that it has taken me to go through this slide. And all of these resources are available to any subject matter expert who wants to do this analysis. So in conclusion, I hope I have motivated the fact that ionospheric augmentations to early warning systems can improve disaster warning time by a lot. So in the Kamchatka case, it was 30 to 45 minutes near Hawaii, but we actually detected the tsunami within an hour of the earthquake. Uh, Guardian is the first operational global high rate multi GNSS system of this kind with intelligence built in, so that the work of the subject matter expert actually becomes relatively easy compared to before. Um, we also provide data to the NASA CDDI system in near real time, so other researchers can actually develop intelligence techniques to spot these signals in near real time data and make the system better. Everything is done online. No one needs to write any software, and I think that's one of the speed of this is one of the main advantages of Guardian. So going forward, we seek to work with other early warning centers in the natural hazards area, especially for tsunamis, so that we can augment their processes and integrate Guardian data and detections into those processes. I'd like to thank our friends and sponsors and partners really quickly. And with that, I'm ready for your questions. Thank you for your attention and enjoy your conference. Thank you.
You. Any questions?
Yeah, thank you very much for this presentation. I think that this is technology. I mean, it's amazing. I think there's lots of potential to going forward with the technology with regards to tsunamis. My question is regarding the inversion that you at some point you said that it's in the future plan. Do you have any plans for approaching the problem analytically?
Yeah, so thank you for your question. So the first cut that we did with this was using an Aussie, and so we essentially we didn't do analytical approaches. We what we did was we integrated uh, actual observational data with simulation, and then tried to invert for tsunami properties from that. So we had mixed success with that. I think going forward, we've looked at various different statistical approaches, but we haven't actually looked at an analytical approach. So yeah, I'm happy to connect with you on that and have a further discussion.
Okay, thank you. Are there any questions? Yeah, we have a question there.
Thank you for a nice presentation. Regarding the tsunami signature that you mentioned, can that be considered as the so-called tsunami forerunners that has been mentioned in Murthy's seismic sea waves book? Has it anything to do with that? And one thing you mentioned, which really struck me, is that you said that these approaches doesn't need a lot of simulation or computational kind of work, and you have reduced it so much so that the 72 minutes before that reaches that tsunami signature is a very interesting one that struck me. So this is not so much as a question, but I mean, this is very interesting. And as a professor was mentioning that if we can connect it with the analytical model, that would be fascinating.
Thank you. Thank you so much for your comment. Like, so on the Forerunner, I'm not entirely sure. Usually, so I know I showed only one time trace, and the ionosphere being a dynamic medium, there are many things that can produce this type of wiggle. So typically, what we do before we confirm something of a geophysical nature or of a tsunami origin, for instance, is make sure that we are seeing a similar signal with correct phasing on a number of different links from a number of different stations. So not every wiggle is classified as tsunami origin. I just use that as an example, but we tend to like look at a pretty statistically healthy sample before we sort of declare detection on that. And yes, I think the intention, just to address the second point that you raised, um, I think evacuating a city or evacuating a region is a very heavy decision. And I don't personally see us as human beings allowing a black box AI to make that decision for us. So I think in tsunami warning, there'll always be a human in the loop. And so the approach we've been following is how do we make the human in the loop's job significantly easier. And so that's sort of the philosophy behind, making these data and analysis available on the cloud online, so that people don't have to go through that effort of doing the analysis themselves when it's already provided to them.
Thank you.
Hello. Is there any necessary condition that how much data we should input for estimation of a precise TEC?
I'm not. I guess I'm not sure what the intent of that question is. In that the TEC that we estimate, it comes from dual frequency receivers. So if they receive phase data on two frequencies, we're actually able to combine it pretty easily and get the TEC data. I guess I don't know if that answers your question, because I'm not sure
No,
if that's what
actually,
you were asking.
like for crustal deformation, we need a denser network to get to reach up to the precise
Yes.
estimation of formation. Is it that in case of TEC also you have to have a denser network? And
Oh yeah, so dense is always good, but we don't need nearly as dense a network as crustal information, because in crustal information you're actually doing positioning, and then you're trying to
yes.
measure along, like along the deformation path. Here, so for instance, I think having two or three stations within, say, like 1,000 kilometer radius is usually, because again, the geometry really helps, and being able to track 100 satellites at a time really helps, because then you can actually cover the sky, and you don't have to have that high density. It's also logistically difficult to have a very high density of near real time stations, because this takes a lot of logistics to like stream the data live, to a data center. So our GDGPS system is the actual hero here. So so we have to, when we're looking at this, we have to be able to focus on doing this with a much sparser set of stations than you would need for measuring crustal deformation.
Okay, thank you.
Okay, thank you very much.
Thank you.
So this session will continue in the
Uh,
afternoon, right?
yes, this session we will resume at around 2 o'clock. Please come back 2 o'clock. We will break for lunch. Before that, I have an announcement. Dr. Tomohiro Takakawa, Dr. Indanita, and Professor Usama Kadri, please hand over your PPTs before going for lunch. Three. Presentations, please give before going for lunch. PPTs to copy. Okay. Please come back at the same place. Lunch is provided at the same place. Please come back at 2 o'clock.
Tsunamis are nature's stealthy. Tsunamis are nature's Tsunami. Tsunami. Tsunamis are Tsunamis are Tsunamis are nature's stealthy giants, capable
Yeah, she said that I have to begin. Did you?
Yeah.
Can you do it?
So we first.
Listo. Paper.
So please stick to the time.
It's not gonna work.
So,
What about you?
me and Linda. Also.
So you're not presenting.
Maybe after.
After.
ITS. ITS week.
Okay. They come. Oh. Okay. All right. We get instructions that we need to start, even though it's just half of the auditorium. So we're gonna start this session with Dr. Tomohiro Takagawa, sorry. And he's gonna tell us about a joint modeling for high resolution tsunami source inversion. Dr. Takagawa is here, yeah? Oh, floor is yours, thank you.
Thank you, Chairman, and thank you coming back earlier. And yeah, today my talk is title is Joint Modeling of Tsunami, an efficient tool for high-resolution analysis. My name is Tomohiro Takagawa from Portland Airport Research Institute in Japan. This talk is related to two papers. One is the Takagawa, Algeria, and Cummins 2024 JGR Solid Earth last year published. And another one is Takagawa, Chida, Fujiki, Kawaguchi published in Scientific Report in this year. So both study is shared key technique. It's adjoint. So what is adjoint? Adjoint is a term of the mathematical term, and it's many aspects. It has many aspects, but in our tsunami research context, it's a new way to compute tsunami Green's functions. So in web form inversion or forecast based on the source inversions, we use Green's functions synthesis. In that case, in a pre-computed stage, we assume many unit sources, unit source A, B, C, D, E, F, like this, and conduct many simulations. So after we can get many Green's functions, A, B, C, D, A. And this stage is a very computationally heavy. However, once we get the Green's functions database, we can easily synthesize the tsunami wave form by calculation of the linear combination of the Green's functions. So this calculation is very fast and light. So it's suitable for real-time applications. So this, however, this Green's functions method has a disadvantage. If we want to get more final resolution, like 10 times final resolution, needs 100 more computation. So that's a problem. And resolution enhancement has its limits. But there is some remedy. The remedy comes from this representation theorem. It's a mathematical theorem. And this theorem states quantity can be calculated by different two ways. So one is using forward model, and another one is using the adjoint model. So this is a derivation of the adjoint equations. We start from the dispersive tsunami equations. This one is from, Baba 2014 ocean modeling. And not appeared here, but Baba-san's equation is the start. It's a forward equations. And no, here. Yeah. Okay, so and the equations are partial integration in space. We can వీడియో కాదు ఈ కర్సర్ పెట్టేసేసి ప్రాబ్లం అయిపోయింది.
Necessary to auto hide. This computer is this right button.
It is already hide, sir.
Already hide?
It is already hide. But it is appearing there. It's okay. Oh. We got some lesson. We shouldn't write such bottom. Anyway, so we derive some adjoint tsunami equations, and this is the comparison. The left-hand side is the forward equations, and right-hand side is the adjoint equations. This is equations are very similar, and finally we found some simple relationship. These equations can exchange each other by the simple variable transformation. So we can, if we have the forward model, we can easily change to the adjoint model. We can make adjoint model this usage of this variable transformation. So this is the flow of the waveform calculation. In the forward model, we start with the tsunami source. We use tsunami source as the initial condition, and time integration by forward modeling, forward operators. And we pick up some values at observation site. So we can get this kind of waveforms. This is a forward model case. And on the other hand, in the adjoint case, we assume a unit source at observation point and proper time integration backward in time by adjoint operator. And finally, we compute some inner product with adjoint state and the tsunami source. So we can get exactly same waveform by using adjoint model. So the advantage can become clear when we need to many Green's functions. In a forward model case, we assume many unit sources. So we need to conduct many forward modeling, forward simulation. On the other hand, in the adjoint case, we only assume a single unit source and propagate by adjoint model and just record waveforms at many places. So we need only one adjoint simulation. And so we can get identical results with far less computation. That is the advantage of adjoint. So now we high resolution made real by adjoint, using adjoint. So before I use adjoint, my research rely on the database with low resolution, like 15-kilometer interval. It's not enough resolution for the M7 or M8 class tsunami source. But now we can use database with high resolution. The interval is 1 kilometer. So we can obtain more, we can recover more finer structure of the source. So I will show some application. The application one is the 2012 Haida-Gwaii case. We use a database with high resolution, and also we developed a joint inversion method. We jointly estimated the fault geometry and fault slip distribution as well. So we can recover this kind of tsunami source from the DATV data. And we made some forecast test. We only use this on 1 hour record for the inversion. And at that time, we can observe only one station. A tsunami is obtained here. And from this kind of waveform, we inverted some initial condition. And we make a forecast. This is the observed waveform, and the forecasted waveform as like this. Blue band shows some uncertainty as well. And I think this is a very good fit, even if we only use on this signal. This is the power of the high resolution database and our inversion method. And this one is application 2, 2012 Noto case. We inverted tsunami source from the offshore observation waveforms, and we can recover some tsunami sources like this. And we reproduce offshore waveforms, and not only offshore waveforms, but also the tsunami inundation height and run-up height as well with high accuracy. So this is the end of my talk. The adjoint code is available on GitHub. So this code includes a forward model and adjoint model, and seawater compressibility and elastic loading effect, self gravitational effect, business dispersion, Coriolis effect, all can be included, and it's suitable for transoceanic tsunami analysis. So thank you for your attention. And if you are interested in use, you can access from this code. Thank you.
All right, thank you for this presentation. We get strict order not to take questions, but because you finished early in time, and because I'm not a good person to ask for to follow orders, so please, one question. If there's any burning question, short one, please. No question? All right, let's thank the presenter again. I have a few questions actually, but I will leave that for the break. Thank you.
Thank you very much.
Okay, next, I've learned to know that there's a change in the schedule. So Dr. Rawichi Kanai is going to present about tsunami estimation using tech data in the ionosphere and Gaussian process regression, as well as functional history matching. The floor is yours. Thank you very much.
Which can I? Yes. It's okay. Yeah, thank you very much.
Thank you very much for giving me this opportunity to have a presentation today. And I would like to introduce a new tsunami forecasting method. It's different from existing method. And also, I believe that our new method can support existing method. In our new tsunami forecasting method, it uses satellite data and also oceanographic data. And we also developed a new machine learning technique to elaborate its forecasting quality. And our new method, again, it can support existing method. And after my presentation, I welcome comments and questions. And at first, I plan to explain main concepts of my new method, but I have a huge amount of presentation slides, so I would like to skip and roughly explain what I did. Firstly, I used ionospheric disturbance data captured by satellite. And after that, I improved my information about initial tsunami using tsunami time series data and combined these two methods to forecast real tsunami. And in the first step, I used the real application occurred in 2011 in Japan. And the second step, I used a synthetic tsunami case in India. And the last one, in step 3, again, I used tsunami data in 2011 in Japan. And firstly, I planned to explain how ionospheric disturbance could occur, but in the presentation in the morning session, another research group explained how it occurred, so I would like to skip this explanation to save my time. And after that, anyway, you can detect ionospheric disturbance when tsunami occurs in the ocean, and in 2011 Japan earthquake case, tsunami case, you can capture this kind of data. This data is captured by satellite, GNSS satellite. You can see there is a depression in electron density near near epicenter. Epicenter is marked this red star mark, but the location of the depression is slightly different from the red star mark location, epicenter. And this captured data, real observed data, is not sufficient to estimate initial tsunami from this figure. So to overcome this problem, I used sophisticated machine learning technique, but it's too complicated in this presentation. What I did is I used the machine learning technique to fitting these data. And using this technique, you can obtain this electron density depression, TC depression from this observed data. And here you can have a highly dense data from observed data. And this depression must have information about initial tsunami. And I would like to show how this information can provide initial tsunami data. Firstly, here. This blue area is initial tsunami area estimated by another group. I obtained this data from Dr. Saito. And TC depression area times 3 the expansion is expressed by red area. And you can see that the TC depression area is overlapping with this blue area, initial tsunami area. So it shows that electron density depression can show the area of initial tsunami. And another point is the tsunami peak location. This black triangle moving on this figure is the weighted average of TC depression. And you can see that this contour, initial tsunami contour peak location is very near this triangle, black triangle. So from satellite data, you can say that the peak location of the initial tsunami can be estimated from the weighted average of TC depression. So from this result, I can say that if you utilize TC depression data appropriately, it's possible to estimate initial tsunami from just from satellite data. But it's not sufficient yet. So to elaborate this information, I developed a new machine learning method. So far, I would like to say ionospheric disturbance can give you information about the initial tsunami size and the location, but it's not sufficient. So it's necessary to refine the initial tsunami information using another technique. And another technique is, I published a paper about this ionosphere disturbance. So you can download the paper from this QR code. And another technique I developed is refinement of tsunami parameters. Tsunami parameter means initial tsunami height or tsunami location, tsunami size. And in this example, I used a synthetic data. Synthetic tsunami case occurred in Indian Ocean or Arabic Ocean. Here, as you know, this is a Macron subduction zone, and there could be a possibility that a huge earthquake or huge tsunami could happen. And in this synthetic scenario, I use these 4 observation point, data GPS buoy point, and using this time series data to forecast tsunami time series near Mumbai. This is also synthetic observation point expressed by blue points. And synthetic tsunami is this one. This could happen studied by another research group. So using this data, I run tsunami simulation using JAGRUS. And this is a result, a tsunami simulation result with such worst case scenario. And using these 4 data points, data points, time series data, I would like to forecast tsunami time series data near Mumbai. But how can I do that? And here I developed a new method. Firstly, I used the time series data within this 30 minutes slot expressed by gray colored area. And firstly, directly or intuitively, you may think that it's impossible to know the initial tsunami parameter values, such as height or the width of the initial tsunami or location. So intuitively, you may think that we should run huge amount of simulation with exhaustive simulation with initial parameter value, a lot of initial parameter values, but it's impossible because the simulation is very computationally expensive. So what I did here is randomly chosen value are used to run very limited number of simulation. And after that, I build an emulator or surrogate model. And using this emulator, I run emulations. Emulation is much faster, much faster than simulation. And using this emulation result, I narrow down the initial tsunami parameter area, like longitude, the location, longitude, latitude, or x width, or y width, or tsunami height. And this is a result of new method. Firstly, I run several simulations, and from here, I built emulator, and I run 1 million emulations. So running 1 million simulation is almost impossible, but in the case of emulation, it's possible to run 1 million emulation. And our new method can give a technique to pick up or to select similar curves. If you have observed curve and if you have your emulation curve, you can pick up which curve is similar to the real data or observed data. Using this technique, you can pick up several curves from your emulation data, like this one. So from 1 million emulation, you can select curves using our new method like this one. But it's not sufficient yet because you have long peaks. This is phase information. So you need to include the phase information in the process of picking up similar curves. And to do so, I differentiated curves. And using these differentiated curves, you can again apply this technique and combining original data and differentiated curve, derivative curve information. This is the result. So selected curves are similar to the real curve or true curve expressed by bold red curve. And you have the other three observation point. This result is from just one observation point. So you can combine these three additional observation point information, and the result is this one. So you can narrow down the location parameters or x width or y width or tsunami height. And using this result, the Mumbai forecasting can work. Here, I have a synthetic observation point, 4 points, and the result is from 1 million emulation, I have only 497 emulation curves, and the result is very similar to the real simulation output expressed by dashed red line. So this result shows that, oh, this new method can select similar curves to the real observation, and using this information, you can run emulation at further observation points. And combine, the key takeaway from this new method is, I don't know. Sorry. Excuse me. Okay. Yeah. From 1 million tsunami scenario simulation is impossible. So I built an emulator, and using that emulator, I run 1 million emulation, and after that, selected emulated curve, which are similar to the real curve or observed curve, and from this result, estimated the initial tsunami parameters, and using these estimated parameters, it's possible to forecast tsunami time series data further observation points. And what I want to do is combine these two methods, satellite data information and tsunami time series pickup technique. And combining these two techniques, I applied a new method to the real world case, 2011 tsunami case. Certainly, we don't know what is the real tsunami shape. So I assume very basic plain tsunami shape, 2D normal or 2D Gaussian model. And from the satellite data, it's possible to restrict or narrow down the parameter range. For example, this is a time series expansion of weighted average point of the total electron content depression, and this is the range of the TEC. So using this information, it's possible to narrow down the range of the parameter values from 1 to 4. And you don't know the tsunami height or angle, but using that technique, our technique, from a limited number of simulation, you can build the emulator and run the emulation and use these yellow colored circle observation point. You can train your data. I fixed only 30 minutes time slot, and using this technique, you can narrow down the range of the initial tsunami parameters, and this is a result. Firstly, this is the initial tsunami. I haven't used any information about the initial tsunami, and the true initial tsunami shape is red dash curve. I assumed the 2D normal, so it cannot be the same with the real tsunami shape like this one. However, the estimated range of the initial tsunami at fixed longitude is very similar to the real one. And again, the fixed latitude tsunami shape is also similar. It's not the same, but it's very similar. And also the tsunami time series forecasting after this one. I used data at yellow triangle point and the tsunami forecasting here, here, here. The shape estimated by our method is very similar to the real time series data expressed by black curve. And another point, for example, here, the time series shape is very similar, although there is a slight difference in the phase. But from here, what I can say is satellite data, ionospheric data captured by satellite has information, and it's possible to refine the information using our new technique. And as a result, those data can be applied to the tsunami forecasting. This approach is different from existing method. So this method can support existing method. So combining this method with other existing method can improve tsunami forecasting quality. So thank you very much. This is our new approach to forecast tsunami time series.
Okay, thank you very much for the informative talk. Unfortunately, we cannot take questions. We have to delay that for the break. We're going to move forward. Thank you again.
Next talk will be Professor Osama Kadri and tsunami early warning using acoustic gravity wave technology toward Indian Ocean deployment.
Thank you. I'll just take use of time to thank the organizers, and also I think it's a privilege to co-chair with the Professor Tanioka. Frankly, I can share with you that I was really happy that Professor Tanioka is chairing my talk, because I thought that we're going to go through time dilation and I can talk indefinitely, but we got the orders that we have to finish so quickly. So all the plans. And if I can ask to keep an ear on the volume, because it might be very loud. Any quick question for the previous session? Because while waiting. Yeah.
You have taken 1 million emulations. From that, you took only 496 final emulations. So, what are the uncertainties in final model or any standard deviation from that?
Thank you very much. The article of only 497 columns from 1 million MD. The uncertainty is expressed by the range of the curve created by 597 parameters.
Yeah.
Am I answering the question?
Like, what is the criteria to take like 496 only? Like there are many 1 million means almost 1 million to 100 seats like final models. In that, I think you took mean value or.
Yeah, in that case, I use the whole data, not only mean value or like median or something. Whole curve data to become 490. So
often to explain to what I did, the new method, but I incorporated all the information from the cloud. All right, thank you. Okay, so I'm going to tell you about acoustic gravity waves. Acoustic gravity wave theory is an emerging field that has applications spanning from oceanic scale to fundamental physics like quantum analogs and time reversal. I'm going to start with a very brief introduction about what acoustic gravity waves are, and then move to one of the main applications, which is related to this conference, about early tsunami warning technology that we've been developing, and then hopefully conclude with something towards the Indian Ocean deployment of the technology. So by acoustic gravity waves, we mean compression types of waves that are moving under the effects of gravity, right? So you can think about it as sound waves, very long sound waves, tens, hundreds of kilometers in length, that are moving in a media which has gravitational effects, which means that the properties of these sound waves would be affected by the gravity. That's why we call it acoustic gravity. Since the Honga Tonga, you could visualize actually these waves. These are the acoustic waves. These are very long waves as well, so we call them acoustic gravity waves. You can see this here maybe in the satellite video. The satellite video here is going through dilation, but maybe in the next one you can see it better, but this is a simulation where these tsunamis are being forced by these waves. I would have a poster on this, so I would be happy to discuss this further. But how are acoustic gravity waves generated naturally? So they can be generated by submarine earthquake, they can be generated by volcanic eruption, they can be generated by landslides, objects interacting with the surface of the water, and even electromagnetic waves. And these have a funny name. Normally they call it apocalyptic horns for a reason, but I cannot specify right now. And they can also be generated with nonlinear interaction of waves. If you are a mathematician, then this would be your pick, right? With regards to the early tsunami warning technology, I would like to give you a brief video which introduces the technology.
Tsunamis are nature's stealthy giants, capable of crossing oceans at unimaginable speeds, turning vibrant coastal communities into disaster zones without warning. In the 2004 Sumatra tsunami, the first waves arrived just 14 minutes after the earthquake, leaving no time to act. What if we could outpace the wave by listening? We've developed a tsunami warning system that uses acoustic gravity waves, signals traveling much faster than tsunamis. Unlike traditional systems that react after a tsunami physically reaches the sensors or only respond to earthquake events, our system can analyze the acoustic gravity waves generated from various events and assess tsunamis globally within seconds. Powered by analytical models and advanced machine learning, it reduces false alarms, building trust and saving lives. Nearly everyone could have been saved if the right hydrophone had been within 1,000 kilometers of Sumatra. To protect the 700 million people in coastal regions, let's expand our warning infrastructure and technologies, ensuring communities are prepared when it matters most.
So the idea is very simple. When you have an effective layer which is going upwards, that generates a surface gravity waves, it compresses the water layer as well, so it generates also the acoustic gravity waves. Now, acoustic gravity waves travel much faster than the gravity wave, carrying that information to an underwater microphone, which we call a hydrophone. This information we want to analyze in real time and try to get the information about the source itself, right? So the strength of or the key maybe of the work that we've done is the analytical work, where we solved the 3D problem analytically. This an analytical solution, an explicit form solution also, which means it's not an integral form solution. So if you have the input parameters, you just put them in, you get the result, right? So it's computationally is very, very quick. And this is, for example, a simulation using, because it's a linear solution, then you can combine things, you can have multifolds. So this kind of simulation, which can be very, very fine, and you can do it with fraction of a second. Whereas if you want to do it with full numerics, for example, then it could take tens of minutes, hundreds of minutes, depend how fine you would go. But in reality, we don't get the we don't have these properties of that fault, right? This is what we want to find. But because the solution is analytical and it gives the relation between the properties of that effective fault and the wave field that we solved. The wave field, it means the pressure field and also the gravity, surface gravity, including the tsunami, right? So because we have that now, we want to solve what is called the inverse problem. So the inverse problem means from the signal itself that is coming fast, right? The pressure signal, we want to find these main properties. And this also we solved quite straightforward because the forward solution is analytical. So it was straightforward. Completely independent of that, we've developed machine learning. It's running completely independent from the model, the analytical model, right? Which is good for confirmation and is good for other things. I can talk about this later on in the break if you wish separately. So at some point we put all these different parts of models together, and we wanted to have an operational software so it can be used at TSPs, Tsunami service providers. The main thing is that the end-to-end analysis can be done within an average of 8 minutes if you have a hydrophone within a radius of 1,000 kilometers, right? And by end-to-end, I'm not talking about from the detection until the analysis is released. It's from the event until the analysis is released. Now, in order, the kind of real-time information that we have, it comes from the CTB2, the Comprehensive Nuclear Test Ban Treaty Organization. Now, one problem is that you can already see here is the ones in blue. We only have access to 4 stations out of 6 stations. So anyhow, it's a very limited number of hydrophone stations that even exist from the CTB2, the other stations. In last June, in 2024, we deployed the software through IPMA. We get this data, and from Cardiff University, we can make the assessment anywhere in the world, globally, and we can automatically we can have also the email alerts and so on. Email alerts look like this. We've added some extra features. We don't deal with evacuation, but we thought that would be helpful for the optimizing the evacuation process. Things like a daylight or night, it might make a big difference if the tsunami is in daylight or nighttime. Things like evacuation times, the population, roads, good roads, less good roads, and so on, and tsunami risk areas, just to prioritize the evacuation process. This is just an example from the Kamchatka. I think I'm too fast for the. This is just an example for the Kamchatka event. Now, you can see the comparison between the observed and the calculated results, which came very fast, obviously. But the only station in the Pacific, there's only one single station, actually 2, but they're nearby. One single station in the Pacific is right here. It's I think around 3,000 kilometers. So you cannot really use that in real time with that kind of station at that distance, right? But we did something, I can tell you about it later on also, that made it also useful until we figure out the problem of number of limited number of hydrophones. We've also tested some cost-effective hydrophones. These exist like there's an Ocean Network Canada. Also the Jamstick and the Donet on the Japanese system, which is quite promising, and some of these are off-shelf products, and they're quite cost-effective. So what we would like to see in order to have a global kind of assessment, we need this kind of a map, right? Is about 30 stations. This is really what is needed. And one hydrophone cost is not, it's not that much. The deployment costs much more, of course. But this is more or less the map for how much stations we need if you want it within a 1,000 kilometers radius, right? If you want it 5 minutes, then you need to go for 400 kilometers. Finally, I want to just zoom in on this region again, so you can see that all is needed is about some of this. These are the stations that already exist. These 3 stations from a CTBTO. So what is needed, for example, in this coast is only 3 stations. However, if you want to go for near field, if you want to minimize the time further, you probably would need to go for maybe doubling, or maybe depending on the location. For some, you go near and so on. So it's an optimization problem. And this optimization problem really has to do with the target end-to-end analysis that you are looking for. And if you want for the near field or the near far field, with all the constraints, of course, the political constraints, logistical and deployment costs, and so on. And with this, I will conclude. Thank you.
Thank you very much. So you have
after the break.
I mean, little bit time, so we can have some questions. Yeah.
Yeah, but of the seismic, you assume that the tsunami is generated by the seismic source, but it's not necessarily from a seismic source. The advantage here is that regardless to the source, right, these acoustic waves that arrive, they tell you how much tsunami you have. It can be a landslide together. In principle, yes. We could not test it because of we don't have. I would really like to talk a lot later on, and we can discuss many questions, because we really have to move on, right?
Sorry, now we have another event, curtain raiser for Indian International Science Festival. After that, ITS business meeting is there. Online participant, please note that remaining 2 presentations we will resume at 5:30.